do another. Here it wants us to calculate the formate ion concentration and the pH of a solution that is 0.5 molar in formic acid, and it gives us our formula here. So it's HCOOH, and it's given us a Ka, so we know that's a weak acid. We know that our weak acids form an equilibrium. In our equilibrium, this is our acidic hydrogen, right? So we have H plus and HCOO minus. And our Ka is 1.8 times 10 to the negative fourth. And then we're also given 0.1 molar nitric acid. So our nitric acid is HNO3. And remember, nitric acid is one of those big seven, where it 100% dissociates. It is a strong acid into H plus and NO3 minus. So we're told we have 0.1 molar. So 0.1 molar of nitric acid means we have 0.1 molar of H plus ions and 0.1 molar of NO3 ions. So here we can see our common ion is our H plus. So I know that I'm starting off with 0.1 molar of H plus. It also tells me I'm starting off with 0.5 molar of my formic acid. And so that leaves my formate ion concentration as our X. And again, we would have had minus X and plus X over here, but we're assuming that 5% rule. So now let's set up our Ka expression here. We would have 1.8 times 10 to the negative fourth is equal to my hydrogen ion, my 0.1, times my formate ion, X, all over my formic acid, my 0.5 molar. So let's set this up. 1.8 times 10 to the fourth, 10 to the negative fourth, times 0.5, and divided by 0.1. So my formate ion concentration is 9.4. So X, which is our formate, HCOO minus, concentration is 9 times 10 to the negative fourth molarity. And then to calculate the pH, remember the pH is the negative log of my hydronium ion concentration, which we know is 0.1. So the negative log of 0.1, and we just actually looked that up, and plus we know that this is 10 to the base units, right? So negative log of 0.1 is 1. pH of 1.00. So if we flip our page over, we are wanting to summarize what is the common ion effect. Well, if we think about it, it's the extent of ionization of a weak acid being affected by the addition of a strong electrolyte of some kind of salt with an ion that's in common. So let's begin to write some sort of a succinct sentence. Here we go. So I wrote down the extent of ionization of a weak electrolyte that is decreased by the addition of a strong electrolyte that has a common ion. Now let's give an example of a salt that can decrease the ionization of HNO2 in solution. So we know HNO2, nitrous acid, is weak. And if we think about the Bronsted-Lowry equilibrium, that sets up a equilibrium forming nitrite and hydronium. So we have our conjugate base, which is our nitrite, and our hydronium, which is our conjugate acid. Now, here we're saying we need to give an example of a salt. So a salt is looking at not an acid, not a base, but using this conjugate base as our last name and using a different cation attached with it. So we could say lithium nitrite. We could say sodium nitrite. We could say potassium nitrite. Any of these are strong electrolytes, meaning they will 100% dissociate. Again, this is not an acid or a base, but it has a first name cation that is not H. It's not an acid. It's not a base. Strong electrolyte. And so let's say I were to choose sodium nitrite, NaNO2. And we can see that these both have the nitrite in common. So here I've got nitrite, I have lots of nitrites. So I have an increased number of nitrite. And Le Chatelier says, well, if you've increased it, I want to decrease the nitrate. And to decrease the nitrate, we're going to shift this equilibrium left to use up the nitrite. So how do we decrease the ionization? Well, we need a strong electrolyte with the same common ion as my conjugate base. So in order to do that, that will help us decrease the ions as we shift our equilibrium towards the molecular form of the nitrous acid. Again, our ions are on the right. If we have a common ion, then we mix it with that salt that has a common ion. That means we have increased our ions. Le Chatelier says if you've increased it, we're going to use them up. We want to decrease it. That's the response to the system, and so it shifts our equilibrium left, decreases the ions to create more nitrous acid. This next part wants to know if the pH increases, decreases, or remains the same when each of the following is added. So we have NaNO2, which is a salt, right? Sodium nitrite. So this is a salt. You know, that's a strong electrolyte. And then we have HNO2, and we know that that is a weak acid. This is where my equilibrium lies, right? So if I have my HNO2, just like what we did up there, I'm just not going to include the water. We know that there's an equilibrium forming my H plus ions and NO2 minus. And we see that our common ion, the NaNO2, so if I increase my NO2 ions here, because we know that NaNO2 is going to 100% dissociate, so I will have NO2 ions and more added to NO2 ions, so that is going to increase my NO2 concentration, right? And what is the response? The system response was, wow, there's a whole lot of NO2 ions. We need to use them up. We need to decrease the NO2 ions. So my system shifts to the left. What that also means when it shifts to the left is that it wants to decrease those NO2 ions. It also decreases my H plus ions. So there will be less H plus. And what does that mean if I have less H plus? That my system becomes less acidic or more basic. So my pH will go up in the number line. If it became less acidic, becoming more acidic lowers the pH. Less acidic gets higher or more basic. This next one, we have methylamine chloride, CH3NH3Cl, and we can tell that this is our salt, right? Because it's a chloride. Like we know sodium chloride is a salt. And then we have methylamine. So if you were to look at, and you wouldn't need to know these names, but we could look at our Appendix D, and we would see that the CH3NH2 is a base. It's a weak base. And it has that nitrogen, which likes to attract those hydrogens. So let's look at the chemistry here. When we have our weak base and we put it in water, so we have our CH3NH2. So weak base forms an equilibrium, and we know that this base wants to grab a hydrogen off of that water. So CH3NH3 plus is the one ion it dissociates, and OH minus, that leaves that water. That water donates one proton, so we're left with OH minus. Now, when we look at adding our salt, our CH3NH3Cl, we know that when we have a salt, it's a strong electrolyte, it 100% dissociates into the CH3NH3 pluses and the Cl minuses. So our common ion here, we can see, is our methylamines, CH3NH3 pluses. So we are increasing this amount, which Le Chatelier says if we're increasing those ions, we need to decrease those ions. We need to use them up, shift this left. Now that also means that these hydroxide ions will be removed. They will be used up just like these are being used up. So we are removing hydroxide ions, which makes this less basic or more acidic. So therefore, pH here is going to decrease. For this next one, we're told sodium formate added to a solution of formic acid. And again, you wouldn't be expected to know these, but you could look them up in Appendix D. So we would see that formic acid is a weak acid, and formic acid is HCHO2. So if we added our formic acid in with water, it's going to form an equilibrium, and it's going to make formate. So again, our formic acid is our proton donor, so we would have CHO2 minus, and it's donating that H to our water to give us H3O plus. And then we would look up sodium formate, which is NaCHO2. And so therefore our common ion is our formate, because Na is plus and CHO2 would be minus. So we are increasing our formate ion concentration, which again is going to shift left. So it will use up our hydronium concentration or remove it. But that means our H3O concentration goes down. And if H3O goes down, that means we're less acidic, right? So if we remove the hydronium concentration, we remove that, it's becoming less acidic, more basic, pH goes up. Let's look at potassium bromide. This is our salt, hydrobromic acid. So, hydrobromic acid, we should know that's one of the big seven. It 100% dissociates into H plus and Br minus. So, there is no equilibrium for strong acids. And if we were to look at potassium bromide, potassium's parents would be KOH or HBr, which are both strong. Therefore, there's going to be no effect on the pH. And let's look at this last one. We've got HCl added to a solution of sodium acetate. Let's look at HCl first. HCl we know is a strong acid, and so it's going to 100% dissociate into H plus ions and Cl minus ions. And then we have sodium acetate. So let's look at NaC2H3O2. Well, so when it splits, this is a salt, so it's going to form our Na plus ions and acetate ions. Now notice we don't have any common ions, so we're not actually looking at common ion effects in this example. But let's see if the pH will be affected at all. If we were to look at the parent of Na plus, that would be NaOH, and that is a strong parent, so that's not going to have any effect. But if we looked at the parent of acetate, which is acetic acid, we know that that's a weak acid. So if we looked at the hydrolysis of C2H3O2 minus in water, we know that, again, acetic acid forms an equilibrium. We get the parent acid, the acetic acid, HC2H3O2, and OH minus ions. So we know that these OH minus ions are the base ions. And so we have our hydrochloric acid, which is 100% forming our H plus and our Cl minus. But notice that when I add the sodium acetate, that it releases base ions. So here I've got H ions and I've got OH ions. So it's going to, these OH will consume some of those hydronium ions. So if it's removing those to form HOH, to form some water molecules, then that means that we are, if we're removing H plus, that means we are becoming less acidic or more basic or increasing the pH. So again, not a common ion effect, but we can still look and see what sodium acetate does. And the sodium parent, be it sodium hydroxide, did not have effect on it, but the acetate forming acetic acid and hydroxide, that hydroxide does have an effect on it.